Welcome back to Rocket Gyan, my fellow space tubers. How are you guys doing? Today I am really very excited because today is the day when we can see another country on the moon. Yes, after Chandrayaan 3, US also tried with the Peregrine lander, but unfortunately it had some issues. We'll talk about it a bit late, but right now let's talk about JAXA's Slim lander. I did the stream when the launch happened, and it was not only the moon lunar mission which was happening at that point of time. It was also the XRISM, which is the X-ray telescope, which is going to observe again the black holes, the nebula formation, and all those things. So amazing times, and JAXA is doing a great, and as a trademark of JAXA, it is, the crazy little missions which they do. This mission is no different. I'll let you know how things are going to be and how everything will look like. So just stay with me, sit back and relax and enjoy the stream. Yes, I am all ready, and I'm really sorry for the delay. Yes, I was setting all things up. It was a bit of, I had some issues with my laptop. I need to change it because for some reason my Wi-Fi is not working. Laptop's Wi-Fi, and I had to connect with the USB Wi-Fi, USB internet somehow. So, uh, just so that was the issue. But now everything is fine. So let me just um, move ahead to the stream. So yeah, this is literally called the Moon Sniper mission. Yes, because literally, okay, let me tell you the overview of this mission. So this is going to demonstrate precision landing on the moon, and this is going to be JAXA's, I think, the first attempt to land on the moon. And if successful, Japan will become fifth country to successfully land a spacecraft on the moon, and this will be the first time for the Japan. So let's talk about this. So it's a high precision landing technology. So basically, what they are trying to aim for is very ambitious. To be honest, they're literally changing the game of lunar landing. They are not saying that okay, we will orbit the moon, look for a flat surface, and go according to that. First of all, if you are looking for a flat surface, then you are kind of compromising the scientific goals. If there is an interesting landing site, and just because it's not flat, you can't land on it. This lander is changing that game. It says no matter what the landing location is, we will land there. And today it's going to demonstrate that, and hopefully it's successful. It will be successful. That's what I'm thinking. That's what I'm saying. That's what I'm hoping for. So yeah, so it says demonstrating high precision landing technology on the moon, basically. So getting down, this is their motto: getting down where it's easy to, getting down where you want to get down. I mean, this is a little bit translation something, so don't go into the grammatical or English thing, but just get a gist of it. So their motto is that getting down where you want to go, right? It's not like you are compromising because of you did not find a flat surface. So this is known as a SLIM project, which is this is the full form: the Smart Lander for Investigating Moon. And it's not only carrying the lander, but it also has kind of the rovers, which is known as, in this case, there are two things: the lunar excursion vehicles. So there are two of lunar excursion vehicles. We'll talk about those also. So yeah, so this is the thing. So weight at the landing time would be 210 kg, and weight at fasting 190 kilograms. That means, I guess, dry weight. So the landing accuracy it's aiming for is within 100 meters. So to aim for within 100 meters is so cool. I mean, how can you just, when you are going for the landing for the first time, and then you are just having this much of ambition? Japan is known for that, and they are known for doing the things also. So yeah, I'm not surprised if they are able to pull it out. But if you will see the landing profile now, it is so interesting, and so, what should I say, crazy, that I'm hoping for its success, but the landing profile itself is like, saying that it won't be successful. I'll let you know why I'm saying that. Yeah, so this is what it is. Let me tell you about, yeah, move on to the next thing. Yeah, so this is the lander on the moon, right? And here you can see how it is landed on the moon. So you can see that flamey end is sideways. Flamey end is not down. And yes, that's what it is trying to do. The landing profile, when you will see, right, it is trying to land horizontally. It will kind of do a belly flop maneuver, but not like Starship from going this to this, but from going this to this. So this is what it's going to do. And talking about the scientific explore scientific objectives. So the scientific objective is exploring the moon. Basically, it will try to land on such a location, which is the Shioli crater, which we will also see. This is the crater in which inside and outside the crater there are meteorite impacts, and there are areas where lunar internal materials that cannot be seen elsewhere are thought to be exposed. They are specifically looking for the rocks called olivine, okay, near the crater, which is supposed to be coming from the mantle, and it's trying to explore that part, that theory in which we said the moon actually formed from the earth. If it did, it will have certain elements of the earth from the, if it is like that case, the mantle will be of that of the earth. So it's trying to explore whether that theory is correct or not, if whether the moon really formed like that as we are thinking of it. So it's going to study that with the help of a multi-band camera, which it's going to have. I'll let you know that also. But that's nothing but a spectrometer, so it will try to analyze the material of those things. It does not have a very long mission life, but yeah, the mission objectives are very clear. So talking about this thing, yeah, the trajectory. Let's have a look at the trajectory. So already this earthbound maneuvers, 2 earthbound maneuvers have been performed. Everything is, I mean, this is already done. These all things are done. Let me tell you, recap the mission. So after that, this was the TLI burn which it did. Then it did the trajectory correction maneuver in between to intersect the moon. After that, the moon, it actually is not, you can see, right, it is not going what should I say, for the lunar insertion directly. It is doing a lunar flyby here. With the lunar flyby, it's trying to get to the moon again. So you can see again a trajectory correction maneuver 3 it is going to do here, and then finally it will arrive at the moon. So why not, now question arises, why not directly inserting to the lunar orbit, right? The reason being, they are aiming for a very compact, lightweight lander. They don't have that much of fuel to waste. So they are trying to do, what should I say, a gravity assist. Yeah, gravity assist to basically slow down with the help of the moon itself. So because of this gravity assist which they did, they are again interacting with coming in the sphere of influence of the moon, but with a much less velocity. With much less velocity, that means much less fuel spent on slowing itself down to insert into the lunar orbit. So images sharp as landing. So talking about images, don't worry about that. CHPD. So that is the case. So first of all, I forgot about greeting you all. So welcome to the stream, Satish, Wildflower, Rohan, Hitesh, and Angel. How are you all, guys? I hope everything is going great. And we are looking for a good set of images. I'll let you know why I'm saying that. So let me finish this. So it will do a orbit insertion here. The LOI will happen here, and then finally again it on the lunar orbit itself, it will stay there for 1 month, which it has already. And now it's the time for it to land. So this is the overview of the trajectory maneuver. Here you can see the animation of it. So this is the lunar flyby which it did, and because of that, here you can see it is actually slowed down with the help of that, and then finally it will do a lunar orbit insertion over here. So very interesting thing, very interesting orbital dynamics in play here. I haven't seen a mission which it actually did a lunar flyby and then did a lunar insertion. So interesting and things for that. And then here you can see how it will do the landing here. So it will be in this elliptical orbit or so, and then finally on the you can say it's trying to explore the landing location, taking the images and all those things. Finally the circular orbit which it is now, and then the 15 kilometer by 600 kilometer, and then finally the lunar orbit insertion, sorry, the lunar landing. So right now it is in the elliptical orbit of 15 kilometer by 600 kilometer. So it will try to come down from there, and hopefully we'll get to see the landing successfully today. Okay, so with that out of the way, let's have a look at what is necessary today: the landing profile. And this is where it is doing something crazy, literally crazy. And just a second. Lifespan, Sumit, we'll talk about that also, so don't worry. So let's have a look at the landing profile. Okay, so we already so first of all, I already told you 15 into 600 kilometer is the pre-landing orbit, which you can see. And here you can see it's a 15 into 600 kilometer orbit. From here it will start the lunar landing maneuver. So but before the start of the sequence, in the orbit itself, it will determine the orbit and the position of the slim from the ground and notify it to the slim. So here you can see, right, it's taking this part, it is taking the images from the lunar surface, and it has a very good and advanced navigation system, because it's a vision based navigation system. So what it will do is it will try to take images throughout its landing profile and determine its location, rather than what conventional landers do. They'll go to the landing point, near to the landing point with the what should I say, trajectory, and then at that the landing point, near the landing point, it will start taking the images. But here it will start taking the images before even starting the landing. So it is trying to do that. It will take images, and it will get to know the position of it, and accordingly it will start its engine. Then finally the power descent will happen till 3.5 kilometers, 15 kilometers to 3.5 kilometers. During this this sequence also, 15 to 3.5, it will have around 50 seconds of coasting phase, in which it will again take the images. Here you can see it is taking images. Here it is again taking images. So it will trying to in between the landing landing descent time power descent phase. At that point of time also, it will cut off the engines, take the images, determine its location, and accordingly adjust its trajectory so that it meets the trajectory landing location which it is going to aim for. This all thing has been incorporated so that the precise landing can be demonstrated. That's why this mission is known as the Moon Sniper mission. And here you can see, so finally it will take some images over here also, and then again at here. So during the coasting period, the lunar surface will be photographed, and then the images will be used to estimate the lunar surface position and speed with high accuracy. So that is there. And then finally it will come to the vertical descent phase, which is here. So after reaching the sky above this thing, so let me just so after reaching that phase, the vertical descent phase, so it will be above. So it's not like, if you have played KSP, it's like going from it's aiming retrograde and then finally landing on the point. So what it does, it will kill all the horizontal velocity at around 3.5 kilometers. It will be above the landing location at that point of time, and then it will hover and try to do what it is supposed to do. So after reaching that hovering phase will happen at around 3.5 kilometer and will be straight above the landing location. It will do the obstacle avoidance, obstacle detection, which it will do slowly and steadily. It will come down, do the obstacle detection at around 50 meters or so. It will do the obstacle detection, and then finally it will cut off the main engines. So after cutting off the main engines here at around 3 meters, so it is also going to switch its what should I say, the sensors from the normal the radar sensors to the laser ones to effectively get to know the the altitude. And then finally, once it is at around 3 meters, it will do the forward inclination. Here you can see, fire one of those thruster, cut off the engine, fire one of those thruster, main leg touchdown here, then the front leg touchdown, and then the stabilization. So this is what I was talking about. This is the crazy part. It will literally cut off the engines above and then flip, do a belly flop, and then land on the side space side of its the spacecraft. So man, this is like next level amazing how it is going to do all that, right? And I have more things for you, so don't worry. Not only it's trying to land here, it's trying to demonstrate that you can land on any surface, any terrain. It's literally aiming for a slope of around 15 degrees or so, so that it's literally landing on the crater edge. Man, this is amazing. Okay, next thing. So as I was talking about, right, it's trying to minimize the weight as much as possible, so and make it as compact as possible. So it has done many things. One of those things to minimize the weight is this, which is the sheet like solar panels, which is very, very lightweight, very reliable also. And you can see it's kind of sheet like, so it's bendable, and you can see it on the this thing, the lander itself, that it is kind of useful. So here this is what I was talking about. So this is the lunar the sensor, the lander sensor, which is the multi-band camera, which is going to do the spectroscopy of the lunar surface after the landing. So it will try to analyze what type of rocks are there, and if the olivine, which is what they are looking for, is present and not. So there is that. And now if you'll see that this is the nothing but the landing leg, the bottom part of the landing leg, the shock absorber. If you have seen the Chandrayaan 3 or the Apollo, it had a flat lander, I mean the this thing bottom, right? And it had crushers which is going to crush like this. But here it's cylindrical, and it's very kind of useful and very unique. And here you can say that yes, they came up with this thing because this was the need of the hour. This is not flat as the conventional lander, because it does not know at which angle it's going to touch down, right? If you have circular this thing, the crushers, the shock absorber, then no matter at which point it hits, it will crush and absorb the shock, right? It's not because it's going to do a belly flop, and it does not know at which point will be the first contact. So it needs certain this kind of dome like structure to do that. And here you can see the this thing, the video also. Here, look at that. It crushes in a very what should I say, great manner, right? So here you can see, right, the crushing is not like, it's kind of it has a pattern to it, and it makes sense for it to have a pattern, so that you know what you are doing in that case, you know how it's going to crush in that case. So yeah, carry the landing tardigrades. No, it does not have the tardigrades. The bear shit had it, the Israel lander, but no, it does not. And also I was talking about it's doing a vision based navigation, right? So to do that, it has developed a special algorithms or the software which uses the facial recognition to recognize the craters on the moon, and it has been so much optimized so that it can be functioned on the computer of the lander, which is space grade computing chip. And the space grade computing chip are actually very less computational. It has a very less computational power as compared to what you are having on your hand on, or what you are watching this stream from, where you are watching this stream from. So it is literally 1/100th the power of your smartphone, the computational power. So they had to very like optimize it so much so that the image translation and the processing is real time. It almost takes around only 5 seconds to get take the images and get to the result. So it's very quick in that case. So this is the video for that. You'll see how it's trying to locate which is the crater it's going to be aiming for by using the facial recognition and facial recognition software to recognize the craters. And if it once it is like, it will find its landing site, it will try to land. So here only it basically is trying to land. So yeah, we'll talk about the landing location also. So yeah, here there's that. The next part. Okay, now let's talk about the lunar excursion vehicles, which is nothing but the rovers of this thing. The belly flop is such a brilliant idea. Yes, Simon, because it's a very crazy idea. If you are going for a successful mission, you should not think on this way. That's why. Again, I mean, they that was the need of the hour. The belly flop is what they have to do if they have to land on the crater and the land on where they want to land rather than on the flat surface. So yeah. So let's talk about the lunar excursion vehicle now. So it has two of these and the purpose of this to explore innovative exploration missions involving planetary surface drift, aiming to acquire exploration technology for going where you want to go and doing what you want to do. So this is the LEV1 mass is around 2.1 kg, LEV2 mass is around 0.25 kgs, and basically what it does is it's a hopper. This one is a hopper. This is the lunar excursion vehicle is a hopper. Literally, it hops on the moon to travel on the moon. Literally does that. And here, this one, the LEV2, is literally developed by a toy company. So if you live in Japan, if you're watching it from there, you can most probably buy it in the stores. This literally is a toy developed by a toy company and is a toy. And it has its own purpose. I'll let you know about that. So the success criteria is to demonstrate deployment function from the SLIM spacecraft and to acquire data related to the landing condition of the SLIM spacecraft. And the full success will be demonstrating autonomous functions and locomotion technology on the moon. And additional success, if they are able to do that, is to obtain the information on the landing site of the SLIM spacecraft and the area around the landing site. So this is the case. So LEV1, which is the hopper, you can see here, right, is going to, yeah, I hope you can see it. It has a direct connection to the Earth, and it has a direct link to the Earth, and it has the activity lifetime of around 40 minutes. So it will try to do the hops and try to collect the data as much as possible. So here, if I'll, yeah, direct communication with the Earth, rough terrain suitable for small rovers, autonomous function, observation of the spacecraft status after the landing. This is what the main function it is. It is having an imaging from the outside of the landing stage. So it has a the landing at this landing. So basically before landing at around 1.8 meters above the surface, it will deploy these two rovers. It's not like it will be deployed after landing. So at above the surface only it will deploy those things. The landing speed will be around 2.4 meters per second, and the LEV-1 will have direct communication with the Earth. LEV-2 is going to send the images of the spacecraft and its surrounding. It will try to take the images of the surrounding, and it has a direct communication with the LEV-1. It does not have a direct communication to the Earth. Literally, it has a Bluetooth communication, basically, what I'm trying to say. So it via Bluetooth is trying to will take images, and it will send it to the LEV-1, and then finally the LEV-1 will send it to the Earth. So it has an accelerometer, visible light cameras to capture the images, and it has a thermometer, radiation monitor, inclinometer, gyro, and photodiode. So it has all these sensors in it to do the actual science over there. So yeah, that is the case. Just a second, guys. Yeah, I'll just be quick on this now. Yeah, so let's go to the next one. So this is the thing. So the rover will be deployed like this. It will be like in the ball configuration, and then it will open up. It has two cameras here and there, and it has this stability tail, which you will see in the video. So this is there. It is developed by the Soraku company, the toy company which it is, and it has two cameras that can image the slim probe. Here you can see from the front and the backwards, and it will automatically run and take the images. It has both front and the rear back image cameras. So it will automatically select the best quality images from the captured images and send them to the ground via LEV-1. Evaluate the result of running on the lunar surface from the data encoder installed on the LEV-2. So basically it does not have any processing unit. It just take images, has certain processing unit to determine what is the best image which it has taken, and then it will just send it to the LEV-1. So there is that. Okay. So this is a video which actually summarizes everything which I have talked about. So this will give you a proper view of what is we are going to look for. So yeah, enjoy. The spacecraft separation, and this is what I was talking about, the lunar flyby which it did, and to come here to the moon, and then observation from the lunar orbit. Stayed there for around 1 month, collect the images and all. So this is what I've already talked about, right? And then it will start its landing sequence, which it is here. After it is on the landing side, it will rotate to the vertical position, again take the images, obstacle detection around 50 meters. If it is going to see if there are any boulders which it has to avoid, and then accordingly take decisions. It found the landing site, and then it will vertically land. Finally, LEV-1 and LEV-2 will be released. This is the final thing. Cut, and the belly flop, tuck, done. This will be amazing if they are able to make it. This is crazy, next level crazy. This is the LEV-1. This is what I was talking about, the hopping of the LEV. And this is the LEV-2, which is the rover. It will deploy and open up and function. And the lander has its own scientific equipment, the spectrometer, which will do the optical observation. So next level crazy, man, next level crazy. Yes, I know the stream has started. Just give me some few more minutes and we'll move over to that. So this is the press kit. We have already discussed everything from here. So I think we can skip all this thing. Is there anything which we have left? I don't think so. Okay, let's talk about the landing site. So it's aiming for this Shioli crater. So this is one of those images which is I think it's LRO image. So this is the crater and it's the rim of the crater which it is aiming for. Literally you can see, right, it does not have a flat surface. Here you can see it's aiming for this location. It is not a flat surface, it's a slope. And one of the reason why it is doing a belly flop is because of the slope. So there is that. So yeah, so if you talk about the moon's perspective, it's going to be somewhere around here, so it's kind of equatorial and it's not on the south or the north pole as we had before. And this is one of those images thanks to Chandra, which the spacecraft took when it entered the lunar orbit, right? So this is those images. So I think that should be it. Now let's move on to the just give me a second. Let's move on to that now.
For around 20 minutes past midnight. During the broadcast, we'll first provide an overview of the SLIM mission to signify its importance from an engineering standpoint and take a look at the science that we're hoping to achieve with SLIM. Then the landing operation will be relayed from around midnight, so do stay with us. We're going to start with a history of Japanese lunar exploration and SLIM itself.
Just a second, guys.
月の重力を使って探査機の加速と減速を繰り返す二重スイングバイに世界で初めて成功。日本はアメリカ、ソ連に次いで月の周回軌道に探査機を送り込んだ国となりました。探査機の速度を自由自在に操れるこの技術は宇宙探査の大きな一歩となりました。
All right, so here you have it. Let me just make myself a little bit smaller so that you can see me. Oops.
当時史上最多となる15種類もの観測装置を搭載。アポロ計画以来初となる本格的な月の観測が行われました。月の地形や地下の構造を明らかにし、世界の月探査を先導する存在となったのです。かぐやの偉業は科学技術の成果だけにとどまりません。月の地平線から昇る青い地球の映像は多くの人々の心を捉えました。
So this is what we have already discussed. So I think you are able to get it, better get it, right?
研究者としての人生が大きく変わったと思います。私はもともと地球の磁気圏のプラズマの研究をしていたんですけれども、かぐやの映像を見たことによって、地球のことだけでなくて、月のような他の星の研究もしてみたいという、もう絶対面白いはずだというそういう意識を。
So this is just an introduction video, right? They are doing all these things. So this is the LRO. 国際宇宙ステーションの後に続く国際月探査 So we all know what LRO has done for the moon and what it is doing, and now Chandrayaan 2 also has joined that race. So yeah, I really hope they shared the Chandrayaan 2 OHRC images to JAXA, but I don't think so they did. So I'm not sure because they haven't mentioned anywhere about the ISRO's Chandrayaan 2 images, which would be much helpful because of the higher resolution. 国際的な月探査であるアルテミス計画に先行して月探査の新しい未来を切り開くことが期待されています。Expectations are high for the SLIM to pioneer a new phase in the lunar exploration. まだ世界で誰も実現したことがない100メーターという高い So again, developed to around land within 100 meter of a target. So this is amazing, right? I hope they are able to demonstrate that. and we will be able to see it. But again, as I mentioned and as I said, it's a crazy maneuver which they're going to do. So, oh my god, I hope they are able to make it.
スリムが着陸するのはミキの海の近くにあるクレーター
Shioli crater.
スリムで採用されたのが斜面でも着陸できる2段階着陸方式。姿勢を傾けながら最初に1本の主脚を設置。その後斜面に倒れ込むようにして残りの足を設置させ着陸するのが特徴です。
カメラが載っているんですけれども、これで月のクレーターを撮影して瞬時に今月の上のどこにいるのかというのを割り出して次の目標地点に素早く修正して飛んでいくと、そういうようなことをスリムが自身で考えてやるというのが非常に重要な技術でして、この部分には注目していただきたいなというふうに思います。
Facial recognition technology, crater recognition
月に着
technology.
陸する際には降りてくる向きや角度にもよるんですが、最大で2トン近くの荷重がスリムに加わります。加えられてもスリム全体が壊れないような設計をするのが一番苦労した点です。
マルチバンド分光カメラなんですけれども、スリムの本体と同様に小さなもので作らなきゃいけないですし、軽くなければいけないというたくさんの制約があったので、それを達成するために観測機器のチームでですね、すごく知恵を絞っていろいろな新しい技術を取り入れて挑戦的なカメラになっています。
スリムが切り開くピンポイント着陸をはじめとする技術は今後どのような形で花開いていくのでしょうか。
ここでやられます技術は将来の月探査におきましても大変重要な技術様式であります。でこれをさらに応用いたしまして日本から続々と探査機を月表面に送り込みたいと考えております。具体的には月極域探査、
Lupex
ローバーであるとか
with ISRO.
宇宙飛行士を活動させるための有人与圧ローバーといったものが計画され
It's
ており
not
ま
a
す。
so this is so we know now that the Chandrayaan 4 mission is not a Lupex mission. Chandrayaan 4 is separate and Lupex is separate, so we need to see if Lupex comes into existence. Japan and ISRO's collaboration.
ますます日本は自由自在に宇宙で活動することができることになろうと考えているものです。これからも JAXA 宇宙科学研究所は挑戦をし続けます。
Alrighty. Now let me...
We will now discuss more about the moon landing with SLIM with our guests on this broadcast. Our first guest is from the SLIM project team, Mori Osamu, in the Department of Interdisciplinary Space Science here at ISIS JAXA.
Hey, Mol Costa. Yes, namaste to you, and I hope everything is... Yes, hi Saidata, how are you? And yes, I do have your animations to go with, so let me switch over to that. I hope that should be good. Oopsie doopsie. Just a second.
Some slides. Here we go. So, from an era of landing where we can, we're going to move with SLIM to an era of landing where we want. So the SLIM mission has two main objectives. Objective A is a technology demonstration of a high-precision pinpoint landing on the moon. With a soft landing by SLIM, Japan will be the fifth country to land on the moon after the Soviet Union, USA, China and India. But the landing precision will be the highest in the world. So conventional lunar landers actually have a landing accuracy of several to tens kilometers, whereas SLIM is aiming for a landing accuracy of only about 100 meters. And this technology is necessary for the era of full-scale lunar surface exploration activities where we want to control very precisely where we're going. The second objective, Objective B of the SLIM mission, is the realization of a lightweight lunar planetary probe system. So SLIM includes innovative weight reduction through improvements to the spacecraft structure, chemical propulsion system, power supply and orbit. And this will lead the development of a lightweight lunar probe will lead to the ability to have an increased payload for missions, such as, for example, sample return missions from the Earth or to Mars, or really anywhere else, because you have more of that weight available for instruments. So from here we're going to look a little bit more at SLIM's configuration and some of the components that allowed it to be such a lightweight spacecraft. So here we have the SLIM configuration itself. The mass of SLIM is 190 kilograms when it's in what we call a dry condition, that is, there's no fuel. And it's 710 kilograms when it's wet, so this is at launch when it's fully fueled. And you can see the features of SLIM's design in these images, such as, for example, the thin film solar cells that stretch across the body of SLIM, and the navigation cameras that, as we'll see a bit later, are a key component to SLIM's pinpoint landing mechanism. You can also spot the two main thrusters of the main engine and the smaller auxiliary thrusters, of which there's 12 around the outside, and SLIM's feet on the right here, which are the small shock-absorbing meshes. So here we have a bit more of SLIM's structural design. Top to bottom here in Japanese is written the PAF rings, which couple to the rocket. After that, there's the tank, which is also used as a structural base of the spacecraft. Below that, there's the deck panels with the landing sensors mounted on them. Below that again, there's the RCS panel, which has the thrusters. Then we have the electrical equipment box and the instrument box with the scientific observation camera. So one of the innovative things here is actually SLIM's tank, because it's this integrated dual oxidizer tank that reduces weight, and then the cylindrical tank itself forms the structural base of the spacecraft, which also significantly contributes to an overall mass reduction of that spacecraft. Now the bottom part of the slide shows the attitude of SLIM during landing. From about 50 meters above the surface, SLIM will rotate to a vertical position and start to descend. But just before landing, SLIM will lean forward so that its lean forward so its rearmost leg touches the surface first. Then the spacecraft tips forward onto its front two legs before stabilizing into this horizontal position. And in the bottom right here, we have the mascot SLIM Moon, which you'll often see on our Twitter feed, @slim_JAXA. And now we're going to turn to the design actually of the SLIM tank, the chemical propulsion system. Now, as I previously mentioned, this is integrated fuel and oxidizer tank, which is designed to reduce the spacecraft weight. If you look at that sketch in the top middle of the slide, you actually have the oxidizer in the blue part at the top. The propellant fuel is in the bottom, and there's helium gas in between. And a lightweight diaphragm separates out these sections, and this is newly developed. It's made of PTFE, which I believe stands for polytetrafluoroethylene, and it's part of the new development for SLIM. So the main engine is actually seen at the bottom left of the slide, and it uses a ceramic combustion chamber that was actually developed here in Japan. And it's designed to use an impressive combination of a wide thrust range and pulse operation. It's not been found anywhere else so far. The high performance also helps the overall mass reduction of the propulsion system. And then on the bottom right, we have the auxiliary thrusters, which have a thrust of about 20 newtons. This is a 12-unit configuration. And by making a different pattern of thrusters fire at different times, you actually control the spacecraft attitude, orbit maneuver, and precise landing. Now we're taking a look at the power supply of the spacecraft. So at the top here we have the solar batteries. These are thin-filmed triple-junction solar cell sheets.
Okay, now I can actually focus on what he's saying.
And they're highly efficient on curved surfaces, such as the SLIM tank. Below that we have the batteries, the lithium-ion battery. The outer casing is made of stainless steel. There's two sets of these cells that are bound by carbon fibre reinforced plastic CFRP plates, and these are designed to stand vibration and impact during launch, as well as charging and discharging in a vacuum environment. And then right at the bottom, we have the integrated power control unit. This handles functions like solar power generation, the power distribution, heater control, battery charge and discharge, and thruster valve operation. So this is actually SLIM's orbit, which performed what we actually call a swing-by orbit, which means it reached the moon. It launched in September, and we actually reached the moon as early as October, at the beginning of that month. But rather than stopping there, we actually swung outwards, and this is the idea behind the swing-by orbit, going to a rather staggering distance of about 1.38 million kilometers from the Earth, before turning back and returning to the moon, where we intercepted again and went into orbit on Christmas Day. There SLIM goes, and there's the swing by. And then we started going back towards the moon on the 6th of November before going into lunar orbit. So the advantage of this swing-by orbit is rather counterintuitively, it saves a lot of fuel, because while it's a very long distance, when you reach these very far distances from the Earth and Moon, you can actually use the gravity of the Sun, Moon and Earth to bring you back.
All this thing is pretty good explanatory, so
it's long, but it's efficient.
Just listen.
Now, once we entered into orbit on Christmas Day, we started to change the orbit to become more circular. SLIM entered originally an elliptical orbit, and then passing between 4,000 kilometers and 600 kilometers from the lunar surface, and then it became more circular and has gradually been lowering since then. So let's look at the demonstration of the technology needed for high precision landing, this pinpoint landing on the moon.
So basically what they're trying to say is, like, all the technology they're explaining us, and all those things which are needed for things
So how does
to
SLIM
make it
actually
successful.
do this very accurate landing?
I've already explained all these things, so it should not be much okay. So
we've gone back to look at the spacecraft design again, and in particular these solar panels, which are flexible and fold around the fuel tank, as opposed to being the flat wings that you normally see with conventional spacecraft. This is very efficient for space, among other things.
So T-minus 41 minutes until the landing starts, guys.
This is because SLIM will be landing in the morning, and it needs more sunlight, so it has to be tilted.
Oh, okay. So he's the I think he came during the he came during the launch also. These two guys were there, so they are that guy is closely related to this mission, so we'll get to know much more insights from him.
We are going to go and look at the technology for the high precision landing, and in particular this pinpoint landing technique. This is the mission movie for SLIM. We're going to do a run through from the launch through to arriving at the moon. So this is a spacecraft separation. And then the first step is both an Earth swing-by, where we use the gravity of the Earth to give us a kick in the right direction. And this is followed by the lunar swing-by that we mentioned earlier, where we actually pass the moon and go out to a much further distance in order to use the gravity of the Earth-Moon-Sun system to pull us back. And now we're observations from lunar orbit. This is part of the vision-based navigation using the onboard cameras. So SLIM's cameras scan the ground beneath it on the lunar surface and identify craters, which helps SLIM know where it is. Now we rotate to a vertical position as we prepare for landing. And SLIM starts scanning the ground again, this time looking for obstacles that would actually be dangerous to the spacecraft should it land directly on them, for example, large boulders. And if it spots a large boulder, it moves horizontally in order to avoid that boulder and to an open space. And then just before landing, it's going to release the spacecraft's two rovers, LEV-1 and LEV-2, And then here is the two-step landing where we land on that back lead first and then tip forward onto the front landing gear.
Amazing, amazing, crazy, always.
These are the two rovers, Lev 1 and Lev 2.
Whenever I see it,
And this is the movement of Lev 1, which is a hop.
hopefully we're going to see those successful landing today, man. This is next level crazy.
Actually have a wheeled format, so it will be moving along the lunar surface with wheels. And Slim is also equipped with a near-infrared multi-band camera, and it will take observations from there. So now we look again at this landing sequence. So the spacecraft starts with a powered descent from an altitude of 15 kilometers and approaches.
We have already talked about all these things, so just listen and have a recap.
Navigation, where it's spotting craters with its navigation camera and autonomously then guiding to its correct location. At an altitude of 7 kilometers, the spacecraft will transition to a vertical descent, and precise measurements of the altitude will be taken with the landing radar. And then finally, the two-step landing with the autonomous obstacle detection that we saw in the movie will be performed before we're safely on the ground. And the maximum, during the power descent phase, the maximum velocity is 1,700 meters per second, and that is about 7 times the speed of a passenger aircraft.
Yep.
And this whole thing will take about 20 minutes, which is sometimes known by the team as 20 minutes of terror.
So talking about the KSP animation, we did not have any landing profile, exact landing profile, so it's a bit rough, so just pardon me for...
So therefore we need to use other ways to find our location over the lunar surface. Now, conventional landers plot their trajectory from the Earth, and then they use their inertial navigation equipment, such as the accelerometers and the gyro sensors, to work out where they are. And then this allows them to find roughly their target location and land. However, those techniques are not particularly accurate, and little measurement errors add up all the way through to end up as a result with quite a large landing area with these conventional techniques.
And this is what has happened with Chandrayaan 2.
What we do is we add in this image matching scheme, which allows Slim to have a much better assessment of where it is on that lunar surface by using its navigation cameras to photograph the pattern of craters below it on that lunar surface. So here's the process of that. We capture images with the navigation camera on Slim, and then an extraction software program is performed to actually identify those craters, which are now circled in blue. And then with that pattern of craters, Slim compares it with its onboard maps, which it's got from previous orbiter missions, such as Kaguya and from NASA's LRO orbiter. And that crater pattern can actually identify very accurately where it is on the surface. And so in addition to its inertial navigation equipment, it has a much better idea of its location, and then it can autonomously correct to find out where it is.
This is the Hayabusa mission.
Now in Hayabusa and Hayabusa 2, which were the asteroid explorers led by JAXA, actual people perform the image matching operation as opposed to inbuilt software. But Slim has the issue that it's not landing on an asteroid, rather it's landing on a moon. And while the moon is much smaller than the Earth, its gravity is much greater than that of an asteroid, and you can't have a slow descent. So as a result, you actually need to do this image matching scheme incredibly fast, otherwise the lunar gravity has just pulled you past the point where it's useful.
Just listen, guys.
Now the other factor you've got to consider is that space computers only have about 1/100th of the capacity of their terrestrial counterparts due to the very harsh conditions of space. So as a result, the team had to develop this image matching algorithm that required only a few seconds of processor time, otherwise you'd miss your chance, on equipment that was not cutting edge. And there's no redo on a moon landing. Once you start that descent, that is it. You can't just pull up and start again, unlike on an asteroid. So now we have a look at a couple of the other navigation equipments on board Slim. The top is the navigation camera. These are two units that are actually placed at different orientations so that Slim can examine the surface both during the para descent phase and during the vertical descent phase when the spacecraft is tilted at a different angle. The middle part here is the landing radar. This is an altitude range sensor to measure the altitude and velocity in the direction of the lunar surface during that vertical descent phase. And finally, we have the laser rangefinder, which is much more accurate, and it's used during that final descent to pinpoint the altitude immediately before landing.
This is the animation, guys. Look at that.
So once we get to the point of the landing, we're actually landing on something that should be a 15-degree slope, and that's dangerous. It's very difficult to do. So in order to land safely on a fairly steep incline, we actually have this two-step landing system was adopted. And this was developed after copious amounts of simulations, both computer and practical, to find out what's the safest combination for a spacecraft like SLIM so that it doesn't tip over. And the ultimate result was you land on the back legs and then you rock forward, as we saw in the movie, to a stable position. Now the legs of SLIM themselves are actually these 3D printed semicircular aluminium spheres, and they're designed to compress to absorb the impact of SLIM landing on the surface. This is a very compact design because much larger missions would use legs with joints, but SLIM doesn't have the space for that, so they have these very compact, crunchable 3D aluminium spheres. Now, just before SLIM lands, it's going to release two lunar excursion vehicles, LEV-1 and LEV-2, and these will be a demonstration of small probe movement technology on the lunar surface environment. So LEV-1 is the bigger of the two, it's 2.1 kilograms, 26 by 40 by 30 centimeters, and LEV-2 is the smaller round ball at 0.25 kilograms. And these two will communicate as follows. The LEV-1 will actually talk directly to the Earth, and it will move through this hopping motion where there is an arm that presses forward onto the lunar surface and it causes the rover to jump. And it has an antenna, so it can communicate its pictures and other information back to
LEV-2 will be using Bluetooth to transfer images to LEV-1.
Spherical configuration into these two wheeled parts, and it will send its data via LEV-1 back to the Earth. This is a close-up of the movement of LEV-1. It has this punching arm that pushes down to the lunar surface. Because the moon gravity is very weak, this is actually very effective, and the rover should jump forward a fair distance before coming back down to the moon.
Yeah.
And this is LEV-2, also known as Sorokyu, and it starts off in a ball configuration, but once it lands, it actually pops forward, and it has these two modes of motion, this kind of crawl,
something happened,
and also a more butterfly-like motion. And so here we are, designing technology from an era of landing where we can to landing where we want.
Yep.
And if you're feeling worried that you didn't manage to absorb everything that was said, Mori-san will be back to take us through the key points just before we begin descent.
I think something great is happening.
So our next guests are members of the private company manufacturing behind the SLIM mission. First we have Okaida Yu, who's from the Mitsubishi
Estimated timing
company.
of landing T-minus 31 minutes until the landing starts. This is not the landing time. It will take around 20 minutes to land, but this is how it is. It will take around 20 minutes, but around 30 minutes until the powered descent starts, and there will be hopefully be another lander on the moon. How cool is that?
Spacecraft can be made lightweight, like SLIM. Then you do have the option of increasing the mass available for possible observation equipment, and also costs such as transportation to the rocket can be kept very low. Such development therefore can lead to more
So
frequent...
basically, talking about these mission objectives, one of those mission objectives was the lightweight, making it as light as possible. They have done n number of things to make it possible, but the main since they are aiming for this crazy little landing profile, so they obviously should have a lander which is not that much heavy. So yeah. Hey, Simeon, thank you so much for that 1999. I hope, we are all hoping for the victory for the Chandrayaan 3 has already conquered the moon. Now it's the time for JAXA's SLIM to do that. So thank you so much for the 1999. Really appreciate it, man.
Year 2026, and visit the moons of Mars, Phobos and Deimos. Spacecraft will land on Phobos and collect a sample from the moon, returning to the Earth in 2031.
Which side of the moon they are actually targeting? On the equatorial side. I have already shared all those things. Shriwardhan, if you have any questions, you can go and see the live, before a little bit
So our next
back, and
guest
you will get
is
to know everything.
Akagi Kensuke from Takura Tomy. Now, Takura Tomy is very well known, but not for spacecraft. It's most well known for being a Japanese toy maker company. The
Yep.
company is perhaps most famous for originally creating the Transformers, the alien robots that can disguise themselves as machines. However, in this case, Takura Tomy have built Lev 2, as
Look at
seen
that.
here. It's a tiny little robot, also known as Sora Cube, and it's one of the rovers on the SLIM mission. And Lev 2 does indeed transform into the second image that you can see that Shin is holding. The rover is about the size of a baseball. It has a honeycomb aluminium alloy shell and starts off as a sphere, as you can see from Akaki-san's model that he's holding. And it then splits in half to reveal a pair of cameras that point front and back. And the two hemispheres actually become the rover wheels. So this little transforming robot will photograph the SLIM spacecraft and also the surrounding terrain before sending those images back via Lev 1 to the Earth. That's the front-forming cameras. And at the back it's even got a little tail for balance.
So the first part was from the toy of the transformer. So it's called a transformation technique that it has been developing. And the second one is this. So imagine that the sea turtles move on the shore, and they're inspired by the movements, and then they try to capture and then try to have that mechanism embedded.
So what I'm hearing is this is a transformer sea turtle.
Yes, that's right.
That's wonderful.
You can actually buy that, Deepak. You can actually buy that. Literally, you can buy that.
そうですね。やっぱりこの空球を作っていく中では、このおもちゃの技術を入れていくとか、皆さんの周りも人大好きなおもちゃが月でも活躍するかもしれないなと思うと、こう普通の考え方というよりかですね、ちょっとこうぶっ飛んだ考え方。
It looks like this has been really creative process to invent this sort of toy.
Something
And
is happening in the background,
and then he
guys.
thinks that this is because of the company's strengths that the toy has been made into the space.
Excellent. And toys like Transformers are incredibly imaginative, so maybe this is a more logical step than we might have previously considered.
And it is unique.
It is unique.
Exactly.
はい、続いてのゲストをご紹介しましょう。はい、どうぞ。
So our next guest is Murata Tomakatsu from the Graduate School of Science in the University of Tokyo.
Transformer sea turtle. Exactly. Look at the description which they have given, right?
So Murata-san is particularly interested in the science rather than engineering behind SLIM and the science SLIM plans to do on the lunar surface. Murata-san has previously worked with a lot of lunar observation data, including that from the JAXA lunar orbiter Kaguya. So Kaguya, which was launched in 2007, orbited the moon and mapped the moon's geology all over its surface. The result were these very high-resolution maps that Kaguya and similar missions, such as NASA's Lunar Reconnaissance Orbiter, LRO, revealed. And you see these key bodies of rock that aren't particularly large areas, but are really interesting, and they could shed some light onto important questions in planetary science, such as those related to the moon's formation. So you have this situation now where you have fairly small but numerous regions of interest that you really want to get a look at. And this brings us to the need for SLIM's pinpoint landing technology and the ability to land on slopes, which enables us to choose a much wider region of possible landing sites and also land on some rough terrain, which is what we're seeing here.
Yep.
And we can actually get close enough with this technology to actually start studying these areas. So this important use case means that while SLIM is a technology mission and it's designed to be testing the pinpoint landing technology on sloped terrain, the spacecraft is also equipped with a scientific instrument, the near-infrared multi-band camera, and it's designed to investigate the composition of the surrounding rocks after landing. And this takes us on to considering the landing destination for SLIM.
Multi-band camera, so it's going to use that.
So Shioli is an impact crater, meaning that it was formed when a meteorite struck the moon's surface. When a crater forms through an impact event, the debris from the deep interior can be ejected, and a central hill forms from those exposed deep materials. So in and around impact craters, we expect to possibly find rocks from the moon's deep interior that have been ejected. And these are often found in mounds in the centre of craters or the surrounding boulders in that region. So one of the minerals that is particularly interesting for this is olivine, which is quite a heavy mineral, and we expect it to have sunk into the moon's mantle during its formation. Therefore, if we spot olivine on the surface, it's probably a mantle rock that's been ejected from the moon's interior.
And we can study that.
And if we could land near one of those olivine-containing rocks and compare their composition with those on the Earth, it can tell us more about how the Earth formed.
Yep.
Moon formed.
And it might be taking like an hour to explain, but he'll try to say it in 1 minute.
Oh, this is the moon's
So here's a moon.
globe. Wow.
And this is the
So this is the shape of the rabbit, and you can see. And this is a pattern that you can recognize on the moon.
So in Japan, well, the rabbit is what's seen on the moon's surface.
That's right. And here he's pointing out the finger, and in that area.
This is where they are going to land. It's in the equatorial region, but again, it's very hard. They are landing on the crater, rim of the crater.
So the Shioli crater is just right there at the spot of the right ear of the rabbit. And then it's trying to land on this exact spot, as you explained. So here it is. This is the rabbit's ear, and there are two rabbit ears. And the bottom one is the western side.
I just love
and
this.
This is where the crater is.
They are literally telling us like where to look at the moon when we are looking at the moon. That
So this
there
is
is
the landing site
the
for SLIM that's going to be on
landing,
this-
lander,
this,
the Japan's
crater
lander.
where we're
Wow,
going to have
look at that.
exposed, olivine material from the moon's mantle, and it's on this sloped terrain, so we have to land very accurately and on a slope.
The crater itself is very small, like 1 kilometer, but SLIM is trying to get that.
理解だけにとどまらないもっと広い意味での惑星科学ですか。
So by going there, by SLIM,
広い範囲でどういったことが今後進展して
will we be able to find out? So this is beyond the SLIM's scope, but could you please tell us about the importance of this research?
私の話の冒頭にご説明したいろんな月の初期の歴史を残しているような岩石に
So one of the main theories for the moon's formation is that it formed during a giant impact with the Earth. If that's true, the composition of the moon's mantle, which is about 90% of the moon, would be expected to be similar to the Earth. So if we can identify a mantle rock, i.e. that olivine, and look at its composition in more detail, we'll learn more about the moon's formation. So Kaguya examined the moon's geology all over its surface. It spotted that near the Shioli crater was a place where the mantle...
another lunar orbiter from JAXA.
And that's why SLIM is planning to touch down in this very small area and examine it with its multi-band camera.
シオリクレーターに降りるってことが先ほど出てきたんですけれども、そのシオリクレーターについてもう少し教えていただけますでしょうか。
Could you please tell us more about this crater, Shioli?
お示ししたミキの海というのがこちらにあります。でこのミキの海の、西側にはそのシオリクレーターという月の、おそらくマントルですね、地下の物質が天体衝突によって掘り返されて今表面に露出している。
So at the bottom of the slide here, we're actually seeing a model for how the moon might have formed. If we look at these cuts, they're actually cuts through a would-be moon. these sort of pizza slices where the core is at the bottom and then the surface is at the top. So going from left to right, the first slice, the green circles are this olivine, which is floating in initially a molten magma ocean. It is thought to have existed on the moon when it first formed. If we go towards the right, we're going to see the moon start to evolve. This is the evolution a little later. The relatively heavy olivine has now sunk down to become sediment and begins to form the mantle. In slice 3, the lighter, buoyant, calcium-rich plagioclase crystals, which were actually shown by little rectangles at the top, were rising to the surface, and these form the moon's crust. So then we only see olivine again if you can dig up some of that mantle, for example, during a meteorite impact, which might have created the Shioli crater.
So in the larger picture, that the scientists will be comparing the formation of the moon and the formation of the Earth.
Yeah, so this
By
is one
looking
of
at
the
the
reason why they are
composition
aiming
of
for
the
that rim, right? And the belly flop maneuver actually makes much more sense when you think, yeah, they are actually aiming for a rim crater of the rim. So this, the crater, the rim will have certain slope like this, and if you land straight, it will topple like this, right? So it does not make sense to land like that. So if you land like this and then belly flop like here on that particular slope, so it makes sense. That's why they devised this crazy maneuver to land, and I'm hoping, so we are around T-minus 18 minutes from the landing to start. It will take around 20 minutes to land, and finally we'll see, hopefully we'll see another lander on the moon. So I'm just hoping, yes, this is a successful mission, because Japan has done it in the past. They are not landed on the moon, but they are famous for launching crazy missions, and the Hayabusa mission was one of those, the asteroid sample return. So the Hayabusa did it before the OSIRIS-REx, and so yeah, this is one of those days where Japan is proving its technological advancement.
So VP Sasaki is the Director General for Human Spaceflight Technology Directorate and the leader for Japan's participation in Artemis. So could you please tell us about what you are doing right now for the Artemis?
Okay, Artemis updates.
So Japan has already said that it will be participating in Artemis. And then there are 3 things that we will be planning on doing.
それから、月の、有人の周回拠点ゲートウェイ、これに対して、生命維持装置を提供するとか、物資を補給するといったものがもう一つ。それから最後が、有人油圧ローバーを開発する。この3つになります。
Okay, so the main goal of the Artemis program is to establish a human presence on the moon, but while doing so, that Japan will be contributing more on the robotics as well. And the first one is the crewed mission that will be setting on the foot on the lunar surface, and also another one will be sending the pressurized rover for crew driving on the lunar surface. So in Washington, D.C. as well, that he has just been to, that they are paying much attention to this Project SLIM. And because this is leading more techniques to be developed for Artemis in the future, so it has like a lot of anticipation and also excitement. And for Artemis project to be going on, that the both sides, so crewed and then uncrewed, so manned and then unmanned projects are important. So they have to be developed in tandem. So the SLIM will just go on and then first focusing on the technology and what more can you do with this technique? So this SLIM's technique will leading us to go to the narrow space or the hidden space. So it will give us much freedom to move around on the Mars surface, on the moon surface. and then there will be more applications in the future. So we will be having more presence, and also we'll be building more trust with the partners.
例えばロケットが打ち上げられることが日本の優位性を保っているのと同じように
And it has been that Japan has great trust building by presenting trustful rockets. And also, we are adding more to this trust in the international partners. So that's this technique will be highlighted, and then it will be developed more in the near future.
的な注目も浴びるわけだし、それを日本として貢献していくのが今回スリムで実証される新しい技術であるということですね。はい。で、その技術を実証した上でね、またその次が期待される。
So what's next? And then what can we say about the projects coming after SLIM?
ということで、今後のミッション複数いろいろと検討していて、今後このスリムが成功した暁には
So we already have a few more things planned in the future. So this will be the critical time for us to look at the success of the SLIM. So does it include the pressurized rover? And yes, the rover as well, that it will go to the place where they want to go. So the pinpoint landing is necessary.
そういうところでこういう無人探査でしっかりと行くということが大事で。
But the rovers can only go to the safer places. So building this technique and then going to the place where it's sort of hidden or it's very difficult to go, and it's still that technology will be useful in the future.
人が行くのは難しいっていうところはやっぱりその無人探査がまだまだその技術を持って実証していく、実際に実現していくっていうこと。
So that's exactly why VP Sasaki has been emphasizing the importance of both manned and unmanned exploration. And thank you very much.
はい、ここでですね、いろいろ質問が来ておりまして。
So now we're going to return to Mori-san, who's going to remind us of the key points as we head towards descent and landing. So here's our summary slide of SLIM attempting a pinpoint landing on the moon. The powered descent is from an altitude of 15 kilometers with 3 thruster boosts and coasting in between. We approach the target site on the lunar surface using this image matching navigation technology, where we're going to match the craters to known patterns on our onboard map using the navigation camera and autonomous guiding control. Then we begin the vertical descent from a 7-kilometer altitude. This includes 3 short hovering times. And we also do obstacle detection to avoid any dangerous boulders from about a 50-meter altitude. And then the 2 little LEV rovers are released at a 2-meter altitude before we do the 2-step landing on the sloped terrain. And we're aiming for a lunar landing accuracy of order 100 meters during this 20 minutes of terror. Landing can be confirmed relatively quickly, but more than that to do with the pinpoint landing accuracy might be determined as much as a month from landing.
Alright, that is something. Month landing they'll be able to determine.
It's very important because we start from the altitude 15 kilometers, and by pushing it forward from that point, it will be going a little bit upwards, and then that will be very useful for the landing technique going vertical.
Yep.
And also the engine will be shooting down, so that energy will put the probe up there. So this curve itself is very much suitable for pinpoint landing.
Amazing. So basically right now guys, T-minus 10 minutes left from the landing to start. They have kind of automatic they have summarized the landing event, and it's kind of very different and very challenging, to be honest, but let's hope they are able to do it. And yes, one interesting fact about this is that this if you don't know, this mission did not like it went to the moon, but it did not do the lunar orbit insertion directly. It went to the moon and then again went to the moon, did a flyby, came back, did the lunar insertion. And now they are aiming for the landing to happen. And I hope the lunar the LEV-1 is operational, because that is a critical part of the rover's missions, because LEV-2 will also, if it survived, will only be able to communicate via LEV-1. So I hope that happens, and LEV-2 will actually going to what should I say, do all those it will click all the photographs, select the best photographs from all those photos. So someone asked, right, if we'll get some good photos from the lander or not. So yes, we going to get it. The LEV-2 task is just that, to go and photograph the landing location and see how the lander has performed, how it has landed over the location. And it has a operational time of around 40 minutes or so, LEV-1 and LEV-2 both. So they are not chargeable. They do not have any battery, the solar panels or something. So after 40 minutes they'll die and remain there. But yeah, the lunar lander will stay on the rim and do all the scientific observation of the rims to get the spectroscopic information.
So we decided to do the longer swing by and then have this slim orbit. So we chose this to have more efficient.
If you see this thing, guys, this is the crusher.
And this has become one of the main goal of the SLIM project.
This is the crusher which I was talking about. So this is kind of a dome shape. Right now it is in the crushed state, but this is a domed shape, and the reason is because they don't know which point will connect first to the ground, right? Contact first to the ground. So they need something which is going to what should I say, consider all the possibilities of the connection and accordingly adjust. So this is what it is, the shock absorber.
To enter lunar orbit straight away.
Usually it is flat, but here it is dome shaped.
そうですね。成功するために。
So what do you think that will be successful?
T-minus 7 minutes until the landing begins, guys. I'm so happy, so excited. I hope this mission is successful and we get to see another lander on the moon.
It has been many challenges and also failures, as we all know.
Yeah, so let's talk about those failures. So recently, the Peregrine moon lander from the US was supposed to land on the moon, but it had issues with it. I'm not sure. Basically, what happened was it had a rupture in the fuel tank. So they did not even get to attempt the land. Not even attempt. They did not even get to see the moon. They went to the lunar orbit, the altitude, but then they came back and now it is bound to re-enter the Earth's atmosphere. And if I'm not wrong, I think they have lost the contact also. It was very unstable in at the starting, but slowly and steadily with the help of engineers and all, they were able to expand its mission lifetime. But it's a very sad demise, to be honest, because it did not even see the moon. Basically, it was supposed to land, but yeah, so moon landing is hard, and Chandrayaan-3 did it flawlessly. So respect plus for ISRO, and hopefully today JAXA will become another country in the recent times. So in the recent times, only China, India, and if successful, Japan will be able to land on the moon. How cool is that?
So could you also tell us about
all the Asian countries ruling the world?
So could you please explain to me a little bit more?
Yeah,
so
look
from
at
this
that
angle,
now.
you can see the 5 legs on the SLIM spacecraft, the rear leg that sticks out the furthest, and then a more square structure for the forward landing gear and middle landing gear. So Slim initially descends vertically and it's going to land on that rearmost leg first. That's the first one that's going to touch the lunar surface. So it lands on the back leg and then it tips forward onto those front two legs.
2 steps.
着陸するというわけですね。でちなみにですね、ちょっと気になる
So
も
you
のが
can
ここに
see
あるん
now
ですけれど
how
も、
why
こ
the
れが
belly flop maneuver actually
Let us see just more.
makes sense now.
吸収するものとなってい
I'm
まして
glad they came back to
これが実
this.
際に足についているわけです。そうですね。この
Yeah, it's one of these little legs. So while a big lunar lander, such as Apollo, actually has legs with a joint that are able to absorb the impact, Slim has these very compact lattice-like legs.
Yeah, this is the chain-like structure which you see. This is the crusher of the leg, which I have already explained.
ここまで質問とコメントの紹介をさせていただきました。さてですね、着陸に向けた
So this
So
is the end of
guys,
the Q&A.
if you are just joining in, let me tell you, Japan is going to land on the moon. The landing is going to start in around 4 minutes.
5 minutes to go.
Okay, 5 minutes. I'll change that timer.
San will review
So,
what will be
okay,
happening
let's
in 2 minutes.
listen to the landing profile.
Yeah,
will be
in
a
the
good
next
one.
few
So this is our pinpoint landing again. The powered descent from 15 kilometers, the vertical descent from 7 kilometers, the search for possible hazards, such as boulders.
I hope so.
So overall, when it starts, it will take about 20 minutes.
20 minutes of terror.
So first it approaches to the targeted position, and then the vertical descent. And it will have 3 hoverings, and it will try to detect any boulders. And then it approaches to the slope and have 2-step descent and landing.
T-5 minutes, he said, right? Let's change it.
So it will be determined relatively soon about the landing itself, but the pinpoint or not, so how precise it was, it will take about a month to process.
About a month.
探査機からスリムから送られてくるさまざまなデータのことを表す言葉です。
So now let us explain about the telemetry. So we will be moving forward to the screen like this, and the telemetry is the
Yay.
data that has been sent from the
Look
probe.
at that Grafana dashboard.
So this is the QL
Wow.
quick look screen, and we'll see this during the descent to the lunar surface, and it will display the telemetry, the data coming from the spacecraft. And we're going to go through just each of what you're seeing here to explain what it means.
So basically, let me tell you.
So this is
okay.
the date and the
He's
time,
explaining.
in top yellow. It's a spacecraft time, but that corresponds almost exactly with Earth time, as it only takes about a second for radio waves to travel between the Moon and the Earth. It's showing the time in UTC, Universal Time, which is Japan time at -9 hours. Now this part is the GNC, Guidance Navigation Control mode, and you can see the different options for the modes, with SPM being sun pointing mode, OCM being orbital control mode, etc. And it tells you what phase we're in at the moment.
Vertical descending mode, moon landing
This
mode.
is going to show us the spacecraft acceleration. It's the actual measured value of the accelerometer is on the left. The estimated value based on the model is on the right, and descending order for the acceleration goes from green through to red. This shows the status of the auxiliary thrusters. The scale here goes from 0 to 100%. And this is the status of the main engine injection, with the scale again going from 0 through to 100%. This shows the angular velocity of the spacecraft along the 3 axes X, Y, and Z. The colours here indicate descending orders of control error, with green having minimal control error. Gosh, we're going fast. This is the remaining propellant. The fuel is on the left, the oxidizer is in the middle, the total is on the right. The fuel to oxidizer ratio is 1 to 0.8. The BAT SOC is the remaining battery capacity, and now we are looking at if this graph looks like this. It's the mode before powered descent. So altitude from the sun is seen on the left. The altitude from the Earth is on the right. This is now what it looks like when we go into the powered descent mode, showing positional information such as the trajectory, white line, and the actual trajectory. Is that right in the red line?
This is the first
this is the
time
vertical
I'm
descent
seeing
mode. My apologies.
that
The last
people
one was
are
the
actually
powered descent mode. This is vertical descent mode.
explaining the dashboard. So I loved that it was made on a Grafana dashboard. So that is amazing. And now, so don't worry guys, I am here. So I'll explain you everything. I did not see the velocity part. So when we'll get to see the scene, we'll get to know. So T minus 30 seconds until the... Okay, there you go. Is this the real... Yes, this is the real one. But has it... no. Phase defense maneuver started. Okay.
So during this phase, as we head towards the lunar surface, we are not going to say a great deal. Please watch the telemetry. And so you can see for yourself how the spacecraft is progressing, and there will be minimal,
and guys, it has started. The lunar landing has been has started. It is in the power descent maneuver. You can see it. The graph is a bit off right now, but just don't worry about it. It will. There is a correction maneuver which will happen. Main engine is at 100% right now. Everything is looking
and
good.
Now the altitude is 15 kilometers and it's slightly up.
Everything is looking good. You can see the in the
right,
KSP animations also how it would look like. So I hope that is supporting for you to know what it is happening in the actual moon lunar orbit. So right now, let me explain you what is happening. So the engines are at full 100%. We can see this these thrusters firing. Don't worry about the line as of now. It's fine. And you can see the altitude is also increasing. We can see the mission control room also now a little bit. And altitude is increasing because it's approaching. It has left the periapsis and now approaching the apoapse, but it will not because it's thrusting. You can see the oxygen and the fuel is decreasing. Here you can see. Here is the full thrust of the engine. Here is the angular velocity.
It will be turned off just for a while.
Okay. So engines will be turned off for a while
without slashing.
Okay, this is happening, guys. This is happening. They are landing on the moon for real.
And on the right hand corner, you see the second control room.
It's happening, and now you can see the correction being taking place, right? Don't worry about the red line as of now. It's not like Chandrayaan 2. It's not like
and in
Chandrayaan
the second
2.
control room as well, that they are seeing the same.
Here you can see the control room, the people at the control room, how they are looking at the screens right now, because everything is done autonomously by the lander itself. So basically here the velocity part is where we are missing right now. I can't see the velocity where it says the velocity is, but we can see the angular velocity, which should not exceed much. It will exceed when it is trying to change its orientation. But right now everything is looking fine. I hope they had that velocity time this thing also, but they don't as of now. So that is something. So we are looking in the KSP animation also. You can see the engines are at full thrust right now. Everything is looking great. It's landing. It's trying to land on the moon. Seriously. Oh my god.
Altitude is now 20 kilometers.
Okay.
And this is the phase of the first boost. And it will keep going for a while.
Okay. So right now you can see still the engines are on and the thrusters are working as is expected. Here you can see that. And we can see this
Fuel,
thing also.
And you can see it on the right top corners.
This one.
And it will have to decrease.
Yeah, it is decreasing. Fine. You can see the angular velocity of Y, Z, and X axis. So there is that. And but where is the velocity? This is something. This is the acceleration part, meter per second square. I think this is a model, and one I think one of them is real. So
the velocity is just about right. So you can see it on the left bottom, and now you can see both A and B are green, and it has been as it has been planned. So things are going
so let me explain you. This is not the velocity, this is the acceleration, meter per second square it is. So here this one is the model one, which is which is the pre-planned one. This is what it is doing right now, and they both are
now reaching 25 kilometers, and it will now go into coasting mode.
That was something. Okay, color also changes. Nice. Okay, right now you can see both of them are expected to change, and now both A and B are red. Sorry, green. This should remain, A and B should remain green only for it to be fully successful. Right now the engines are turned off. It is taking the images of the lunar surface and making sure that it is in the right place.
It started to scan on the moon's surface, so it's looking for the exact place to land.
Z is not the velocity. I mean, we only have the acceleration part, so there's that. But don't worry, you can see in the
is just about 25 kilometers.
And we have the engine ignition, and it is supposed to happen as if, yes, it is happening, guys. It's working as expected. It has analyzed the images from what it has taken in the coasting phase, and now it has it will be doing the correction maneuver so that it can land on the perfect place it has to land. A and B should remain green. They are remaining green.
Into the second phase of boost. So now you can see the engine firing.
Everything is looking as expected. Wow, this is working, guys. Finger crossed. I hope they make it. Okay, power descent maneuver is still on. Now it is coming down, but again, now we should worry about that red line, if it is apt or not. But you can see on the animations.
Now you can see the planned trajectory.
KSP animations. I hope you like it, guys. Just give this stream a like and send your best wishes to the lander so that it lands on the moon.
Trajectory.
Okay. So things are looking great. The thrusters, the angular velocity, although this thing, the Y, omega Y, which is the angular velocity on Y, is red. I'm not sure what I think that is. Oh yeah, I understood. That means it is in action right now. The Z axis should not be much, so that should remain like that. So everything is looking fine. Still, it is a bit off, but I think that should be great.
下がってきています。
そうですね。だいぶブレーキが効いてきましたね。最初軌道が先ほどお話しした理由で上がってたんですが、はい、もう落ちてきましたね。
And don't take that KSP animation to be like
start to descend a
the
little
model
bit,
is
as you can
a bit
see
rough
on
there.
the
So,
right
yeah.
side. It's
Hey,
still
Rifat,
doing the
how are
second
you?
boost.
ブースト実施中です。
So things are looking great. It's still at 100% fuel. Now again it will cut off its engine and do the image scanning once more once it is on the the landing location. So still A and B are green. That is what it should be. Those are the acceleration metric. We don't have velocity metric for some reason, but we do have acceleration metric. So we'll see how it works, if we were able to land on the moon. Again, reiterating the fact, we will get to know if they landed on the moon or not, but we don't know if the pinpoint accuracy of that we'll get to know after a month or so. So right now
Fuel's also decreasing, as you can see on the right top corner. And now you can see 96.6 kilograms of fuel, and it will be about 10 kilograms or even a little bit slightly more. So that's where we are aiming at.
Okay, so it's decreasing.
So it will not be completely empty.
Yeah, fine. Awesome. So right now again you can see the like acceleration metric. It is as it should be. Things are looking great. Angular velocity y, z, and x are not disturbing. Y is disturbing right now because it is accelerating. So
velocity
that is expected.
Increasing. That's on the left-hand side, and
it's not velocity. It's acceleration.
Decreasing. That means velocity is getting a little bit more in number.
It's not velocity, guys. It's acceleration. So velocity metric we don't have, and that was supposed to give us the actual idea of what is happening. Respect plus for ISRO for showcasing everything on the screen.
Continue a little bit. We are still on the second boost stage.
Things are looking great. We can see the line matching now, guys. It's not Chandrayaan 2 which is being repeated here. The line is matching. We are looking good. We are looking at the right direction. The model, so B is nothing but a model, the pre-planned trajectory, pre-planned acceleration, and the A is what the real time it is experiencing right now. So both A and B, if they are green, that means they are looking good. They are going great right now. And we are so basically things are looking great. The engines are at full thrust. It will go right to the landing location. It will kill. It's right now killing all the horizontal velocity. Once it kills all the horizontal velocity at around 3.5 kilometers above the surface, it will hover, and it will vertically hover. So it has killed off all the horizontal velocity at that point of time. It will do the obstacle avoidance maneuver there and land. And the landing trajectory is amazing. It is crazy by itself. It will do a belly flop maneuver there.
And it's now above 15 kilometers, and it will continue a little bit longer.
Okay. The total fuel which you can see right now, 140 kilograms, it will come down to 10 kilograms after landing. So that is what we are expecting. Everything is looking great. Oh my god, this is amazing. One more lander on the moon, guys. Let's cheer it up. Let's hear it. I'm very much excited for sure. I really hope they had the velocity metric, because that would have given us a proper idea of what is happening there. But I hope the animations are helping you guys, the KSP animations on the right hand side, so that you get to know what is actually happening on the moon. Hopefully on the lander side, right? So it's coming down. It's on the 15 kilometer mark from where it started, went up, and then came down. It's nominal. It is what happens in orbital mechanics, orbital things. So don't worry about it. Now it is trying to. You can see the altitude decreasing, and okay. Yeah, everything is fine. So altitude will decrease now, and the downrange, you can see it has kind of killed all the horizontal velocity, almost all the horizontal velocity, and we are looking
Still
good
the
right
second
now.
boost.
At around 7.5 kilometers, it will. I think it will again do that imaging one. Costing phase will happen. So engines are pointing right now. Once it is above the landing location, it will point down. But once it comes near to the surface, it will do the belly flop and land like this on the sideways.
So when it goes below altitude 15 kilometers, it will start the coasting again and then try to do the image scanning.
Right now you can see in the animations, it is doing that kind of. Don't go directly to the animations. And there you go. The engines have been cut off. It is doing the image scanning. In the animation also,
now
you can see that
the engine has stopped like 0%. So now it starts cruising.
It is going good, guys. Everything is looking great.
The surface.
Look at that precise graph. I mean,
So
wow.
image scanning right now.
Awesome. It's doing the image scanning.
And soon we'll probably see the third phase of boost.
It has oriented again. Now it will come vertically up. Hey, there you go. Engines have been relighted again. It's going good. It's
Now you
as it
see
is
the
going as it
engines is
should
on
happen.
now, 100%, and now the third stage of boost has just started. And
Okay,
the
one
third
more thing
one
is
will
there
not
that the
be
engines are not throttleable. Engines are not throttleable. They are fired in pulses to control the actual thrust. So that is one thing which you will see. You can see right now it's pulses are being fired. That's why the velocity, the acceleration is getting disturbed right there. But it's above now. It's still at the power descent maneuver. It will change to the vertical descent phase very soon. It's still going right now. The acceleration is as expected. We can see A and B both are green. Right now the pulses of the engines are being fired because the engines are not throttleable.
The left top is PDM. It will soon change
At 3.5 kilometers, it will change into vertical descent mode.
into VDM. So
Yep.
PDM will change into VDM.
It's happening. Oh my god. Okay. VDM is going to happen very soon. At around 3.5 kilometer, it will do so. So 90.6 kilograms. Battery percentage 82%. You can see
Now
the pulses.
approaching altitude 5 kilometer.
Okay. At around 3.5, it will going to do the. Now the actual tension starts. Here you can see the actual thing, how it is on the moon.
Now it's been changed VDM.
VDM has
Now
happened.
starting the vertical descent.
Okay. We can see right now it's just on the landing site vertically up. It will come down slowly and steadily and then do a belly flop. So it has killed all the horizontal velocity now. It is just going down and you can see actually the slope. The slope is there. You can see the slope on the
So x-axis
right hand side of the
is
image.
the west and the y is south. Now it started vertical descent.
It has started it. Things are looking good.
これもしばらくパルスーン車ですね。今数字が 100%
You can see 2.5 kilometers above the surface right now.
100% になったり、またそれ以外の数字になったりと切り替わってます。これパルスーン車をしているのでこういった形で。
You can see the pulses being fired on the engines. That is totally expected.
これで500メーターぐらい
It's coming down 1500.
で500メーターのところで
Oh my god, it's happening, guys.
It will descend
1200.
around 500 meter and it will start the first hovering.
It's doing the vertical descent. You can see in the animations also, guys. KSP animations. 600 meters. 500 meters. Yes.
Around 500 meter, it will start doing the first hovering.
The first hovering you can see the avoidance on the screen. The obstacle avoidance maneuver it did. It will fire
It
all
will
the
be a
thrusters.
short time, but this is the first hovering.
It's still stable on the 500 meter, guys. I think it's gonna make it. It's gonna make it. We can see it's still at the 500 meter mark. It's stable there. So it knows what it is doing. It's able to control itself. There is no error, nothing. Oh my god, this is happening, guys. I hope it's able to make it.
It starts to descend again.
Now it's 400
and
meters.
next aim
300.
is 50 meters.
250. 200. 150 at 50 meters again it will hover. And
so at the next point, it will scan again to see if there are
please stop.
any obstacles
50
or
meters. Stop. Stop. Stop.
まもなく50メートルに到達しよう
Stop
というところです。
and yes, 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 it has. Oh my god, it's happening, guys. It's going in. It's going for the.
This is the second
Now it
hovering.
will deploy the rovers, the lunar excursion vehicles. It is so
Now
precise.
it's looking for the safe place to land.
It's in control. Yes, those LEVs are deployed, and we.
これで高度2メーターぐらいのところで第3回のホバリングを実施し、これでレブですね、超小型ローバーを放出します。
And guys, 0 meters.
一気に降りて2段階着陸をするという形になるかと思います。
Around the 2 meters, it will release the lev and it will land.
Data stopped
Two-step
coming.
landing is expected.
Okay.
モードが、今 MLM というモードに切り替わりましたので、
We are getting some data. Oh.
Now you see on the left hand side MLM. That means it has landed.
No.
From the
Wait.
telemetry,
Wait.
it shows
Wait.
the sign
It's not in the
MLM.
good orientation. It has kind of landed, but not in the good orientation which it should be. The solar panel should face up. I'm hoping that we need to wait, guys. We need to wait if that was successful. And there you go. In the KSP also, the landing has happened. Oh my god.
From the telemetry, what we see is the SLIM has landed on the slope.
It has landed, but I can't see. You can see here the solar panels are facing the sideways, which it should not. This should be facing up. It should technically topple down here, but it has not. And I think it has deployed the LEV rover, so we'll get to know more about it. We are just waiting for the confirmation now whether it has landed or not. It's not upside down. It's supposed to do a belly flop, but it is not supposed to do a belly flop on this angle. The first it was supposed to touch on this point, and then it was supposed to land topple down and land here, so that the solar panels are on the up and the engines are on the side. The configuration, I mean, they literally came so close, and 43 kilograms of fuel left. Now please translate someone.
It looks like on the telemetry that SLIM is on the surface of the moon.
I hope so.
一連の動きは大体想定の
But whether it is intact or not. Problem is we don't have the velocity graph. How we can do that?
スリムの状況を現在確認中です。
We are now checking the status.
Okay, please. I hope it is fine.
はい、画面の上では、スリムは月の表面に、到達したと思われますが、現在、状況を確認しております。
So in my animations, it has landed. Not sure what has happened in the reality. So we have to wait.
From the screen, the SLIM is on the moon. We are checking the status right now.
It does take some time. Sometimes it takes time to confirm the this thing. What is the status on it? See, because the problem is the A graph you can see, right? It is stuck at 1.627. It should not. It should. If the telemetry is still coming in, it should come down because the acceleration is not still this much of constant. If it has stopped, it is on the ground.
We are
safe.
now checking the status of the SLIM.
It should
it
come
looks
down.
like it has reached on the moon from the screen that we see, but we are checking the status.
Okay, so that 1.625 telemetry, right? it should be 0 right now if the telemetry is still coming and the lander is still alive. That's what I'm hoping. I mean, the impact could mess up the communication sometimes, so it might take some time for it to recover. So we are still hoping. From the graph which we can see, it's not on the right configuration. It should be on this horizontal
We're still
level.
checking the status.
But still hoping for the best. No, Wildflower, because it's a constant one, right? If it is changing, then I may tell that okay, it's rolling or something is happening, but it's stagnant, like the telemetry has been lost. No thrusters are also firing, so the thrusters also should fire sometimes. Okay, it is changing. It is changing. It has changed. So maybe it's it might be rolling. But the thrusters are not firing.
The status.
We are still getting the data though. That is great. 1.630. But it should not increase. It should be 0 right now. It might be rolling. Yes, you are right. Wildflower. Because it has landed on the slope. And if it is not right, then... but the angular velocity should tell us that it is rolling. Angular velocity is not telling us that. I hope it's okay. It's red. It's red now. What does it indicate? Yes, Aravel, maybe the telemetry bitrate is slow. Yeah, that can also happen. I'm just concerned about that it has gone it has not this thing. These legs should be on the ground. But it is not. These legs. It's on this side. Okay, it's changing, it's coming. But it should be 0 at the moment.
We are still checking the status, so please wait. We are still checking the status, so please wait.
Yeah, we are waiting for the status update. Yeah, the suspense is killing me now. 1.627. So it's kind of some sort of acceleration is there. Some sort of acceleration is still there, which it should not have. Although the angular velocity says everything is 0. What sort of acceleration is happening then?
スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube
battery percentage, see that 74%, quickly coming down. I hope it's not recharging also.
スリムの状況確認のため、0時30分で番組を中断いたします。スリムの状況確認のため、0時30分で番組を中断いたします。なお、後ほど、ただいまご覧いただいております YouTube ライブにて、記者会見を中継いたしますので、開始までしばらくお待ちください。
So we are still checking the status. So we closed this session at 12:30, and later on the same link and the same website, that press conference will start. So please come back to the press conference.
No, bro.
We are still checking the status.
We are not coming where we are staying here. Please don't end the stream. Pratim, you are, what should I say?
We are ending this program at 12:30, but we are still checking the status. Later on this channel
angular velocity.
Later on this channel, we will
Z-axis.
have the press conference. So please wait. We are still checking the status, and the press conference will start shortly. Thank you.
はい、スリムの状況確認のため、0時
Bro.
30分で番組を中断いたします。
1.628. The acceleration is increasing for some reason. Maybe it's sliding down. That may be the case. In that case, there won't be a angular velocity, but there will be some sort of acceleration because it is sliding down on the slope. Maybe. Again, not sure. But now we can see the z-axis 0.1. Some sort of acceleration is there. It's not a good sign when the live stream is suspended without even telling us what has happened. It's not totally a good sign.
So we will end this program at 12:30.
People are not looking happy.
The press conference will be held on the same link. So please wait until the press conference begins. We will be ending this program at 12:30. Thank you.
Yeah, they don't look happy. Don't worry guys, I'm not going anywhere. We'll analyze it as much as possible, seeing the data, whatever is coming, to see what has happened.
0時30分になりましたので番組を中断いたします。ここまでご覧いただきありがとうございました。
For watching.
Thank you very much for staying with us.
Nah, bro. No. This is not good. I mean, everything was good until that 50-meter point. So there's that, but okay. Let me check if we can see what has happened. Okay. Those Japanese don't have that much of expression, but yep, it did not look good. Okay, we'll see the okay. 107%. Okay, one thing which I again said was that deceleration is now just okay. As he tweeted something. He's a great thing. Batteries on Slim are slowly discharged. It may be in an attitude that doesn't get enough light on the solar cell right now. Yep, that's what I'm saying. That's what I said. It should be like this, guys. It should be on the surface like this. But what has happened is it's not actually. So right now, if you'll see, right, I'll let you know. So basically, it's the first contact of the lunar of this lander should be this point, this leg. Okay, just a second. So this should be the first. Yeah, Scott, maybe, yeah. Scott might tell us. He is tracking it, right? On the moon is fine, but at what condition? We can see that here also. Here. It is good. It's good. The signal is still coming in. So that means it is still alive, but may not be in the correct orientation. So there's the proof, guys. At least they made it safely. It's not broken into pieces. And the crazy part was the landing, the belly flop, which they had to do. Now anything can happen at that point of time. But the thing is, it is still alive. Okay. And still we are getting the data, Slim and the Lev 1, we are getting it. So Lev 1 is also alive in that case. So that is great. This is good. This is good. but again the Dopplers cannot suggest whether it has landed on the correct orientation. The problem right now is the orientation. That is the main problem. So the thing is that okay, what I was saying, yeah, let me tell you that now. See, from this image, this was the supposed to be the first point of contact. Okay, this was supposed to be the first point of contact, and from here, after this point of contact, it was supposed to topple on this side. Okay, but if we see the orientation, okay, what has happened? They ended? Oh, bro. Where is the previous? How can you do that? We can check our stream, so that won't be a problem. Is it so? How can they cut in between? I don't know how to do that. They have not started it again. Not sure. Okay. Let it be. We can start. We can see our this thing. Okay, I'll mute this one. So yes, here. Okay. So we can recollect the landing time. Okay, let's revisit this thing and see how it has happened. So here you can see, I'll go into this mode. Wait, so that you can better see it. All right, not this one, yeah. Okay, yes. So here you can see, right, this thing. So till 500 meter everything was fine, because the main thing happened at the 100 meter mark. So this was looking good. Everything was fine. 100 meter, yeah. Here it started dropping, but at 50 meter it still again was stabilized, which we can see it here. So this was good. Then what happened? Okay, it was looking good only, but here, okay, now here it started dropping. The first point of contact was supposed to be this part, okay, and now see what has happened. This part was supposed to be the one. Okay, we'll see. Okay. Let me revisit and see the acceleration meters also. Okay, the engine fired before, okay. I don't know why it went inside. Okay. The orientation is still that only. Here, there should have been a this thing spike. See the issue, I'll tell you now. Now the issue is either it has toppled a lot than expected, because the first point of contact was supposed to be this part, this little part, right? But it is and it should then be just after this point of contact, it should just be on the ground flat. But ironically, the first point of contact is in the space right now. First issue which we have found is Yes, Baba Yada, router problem it was there. I did not land on my side. Okay, it should work now. It should work. It should not be a problem. Okay. Please, yeah, please refresh. It will work, guys. Yes, I was actually using my. So basically, my Wi-Fi is not working, so I'm using my phone as a Wi-Fi source via USB. So that happened. That caused phone, because of the phone it happened. So it's working now, right? Yeah. Okay. Cool. Great. So yeah, what I was saying. So I was saying two things might have happened. So this was supposed to be the first point of contact. Okay. Now this is in the space. Now it can be caused because of two things. First, this did not make the first contact, and this point made the first contact, and it remained in this position because of the regolith. The regolith might be denser there. So because we saw in that demonstration also, when he when he was showcasing how it will land, right, it was in this position. Let me share that thing with you. That was amazing actually. We were able to see that, and it actually happened today. Okay, where is it? Where is it? Where is it? Yeah, this one. See, this is supposed to be like it should be landing like this, with this making the first contact, right? Here, see this thing. Okay, this thing actually happened, right? See, it's like this only, right? But the problem is, if it was like this with the engines down, then that was fine. But the problem is, it's like this with the engines up. It should not be like that. He demonstrated somehow the future today. Yep, it was the case. I hope it's working now. Yeah, great. Okay, so this yeah, so this was supposed to make the first contact, and then it was supposed to topple. See, like this. That made the first contact, topple, and then land. Like this. So so I was saying there could be two possibilities in this case. So first is that this rather than this making the first point of contact, this made the first point of contact, and it might get stuck. Lunar regolith might be denser over there. First point. Second, it might made the first point that might have been this point only, but the force must be just too much that it rolled over, and it rolled over and caused it to be up like this. And we could see in the this thing, the acceleration graph, that we are getting some sort of acceleration here, but we are not getting any sort of acceleration from these angular velocity part. So this could demonstrate that it's not having any sort of rolling part, orientation change, but it might be sliding because it has landed on the slope. And in the KSP itself, right, if you'll see this thing, my this thing also slided when I landed. See this thing. Ignore all that destruction. That's the KSP way of landing. But see, after that, I also landed on the some sort of, resemblance is there. We can make it out. I also landed on the slope, and it then started sliding. Might be this has happened in real life also. We don't know. Because when it is sliding, it won't have any rotational part, but it might still be having this thing, the acceleration. Then it stopped in KSP, but what about the real life? I think it might have rolled backwards. Yeah, it might happen. Yes. The problem is the telemetry itself was not very much what should I say, informational. The best information is the velocity metric, and that was not there. So let's see if we have any other. Okay, JAXA tweeted something. until the press conference. Okay, let me see. Open this also. Okay. Yeah, so we don't have anything on the... See, the thing is, okay, I'm sad. Are they tracking it? We can see that they are. Okay. We can see the Dopplers in that case. Are they tracking that? No. Are they tracking the slim lander? Slim definitely landed safely. Okay. We are getting a signal. That is not a problem. I need to see the Dopplers when it's... Yeah, I think... is fine. Yes. It is my voice is clear, right? Sound is there. Yeah, okay. So okay, so the Dopplers, and then it happened. Okay, wait a second. I think after that this change happened and it caused it. Okay. Slight deviation, but still strong signal. Okay. So signal is still coming. That is fine. It is stable. Yeah. See, the Dopplers kind of tell us if it was having a problem with the landing, and basically what happens with the Dopplers is that it tells us the change if there is any sudden acceleration or something, right? We'll get to see some spikes or some things happening on the Dopplers. But since here we can see it's a stable signal which is coming, that means it's on the ground and it is stable. But in which orientation? That is the main problem here. The problem is not that it is not there on the moon. It has landed safely. I'm saying again. So I'm not sure whether it will what should I say, be transported. No, it will be told as a successful mission to land on the moon or not, because it is landed successfully. It is still we are still getting signal from it, but the problem is with the orientation. Now will this be a successful landing? Still on the site. Okay, is it so? Which site? Let me check. See, here also we can see the signal is up. Left signal is up, and according to the live signal, okay, this something happened. Okay, lev. Okay, they have turned the lev. So lev is also working, guys. The slim is working, and at least lev is on the ground and it is working, and it is on the ground safe. Now at least something is on. I think this will be marked as a successful mission. This will be marked as a successful mission in that case. Okay, he's changing it. Fine. So lev is working, so that is a great sign. Because if lev is working, in that case the lev 2 will be able to take the images of the spacecraft of the lander, what's the orientation and how it is, and it will send it to lev 1, and the lev 1 will send it back to the earth. So we'll get to actually know the orientation from the pictures itself, how it landed and what actually happened. I think it counts as a soft landing. Orientation might be an issue right now, just that. So I'm hoping we are going to see some announcement. You said, right? Very brief and in Japanese. What was that? Japanese is not a problem, but what was the announcement? No final confirmation. How? I don't know, man. Soft landing success yet to be confirmed. Fine. Okay. Where is it? No tweet from this account, Slim account. Need to check the Slim account. So we have a tweet though. Yep, no tweet from here. We'll have to monitor this thing. Telemetry got interrupted. Don't know if that is the final orientation. It's entirely possible that it can't get illumination on the solar panels right now, but will get power once the sun moves west. Yep, that is true though. Okay, I think this we can mark it as a success. Orientation feels like everyone, what we can see is that orientation is the issue. That's it. Not sure what has landed, but I think it has landed successfully. If it has, oh my god, I think we can count it as a success only. Oh man, when it will start. Although it did not look like what should I say? So if I open up the mission parameters, right, the successful parameters, what was there? What was supposed to be done? What was supposed to have been done to make it a success? It was there, I guess. High precision landing technology. I'm not sure about the 100-meter part, but they did land on it. This though is fine. Success criteria: realize a soft landing minimum. Realize a soft landing on the moon with a small and lightweight spacecraft. Accomplish the following 2 items. By conducting an actual lunar landing descent, verify the vision-based navigation, which is essential for high precision landing. Develop a lightweight spacecraft system and check its operation in orbit. Achieve high precision landing within 100-meter accuracy. The navigation system and the guidance rule operate normally, and the achievement of landing accuracy. Okay. This, I think they have done this. It does not say that if it is, the soft landing is done because it's still alive. We are still getting the signal. Only thing is the orientation. So I think we can say it as a success. If it has, clapping for them, because in that case, wow, first time They attempted a landing and they were successful on the first attempt. Till 50 meter it was looking so good, everything was in control. Japan is known for crazy things, and this was one of those. So only problem, you know, which happened was because of that crazy belly flop maneuver which it was supposed to do. So I guess it landed where it wanted, but like it landed on the slide, on a slip and slide, even though the touchdown was smack on lot. Yeah, it might be. Live ho gaya kya conference? Is it so? No. Still there is no official tweet from JAXA. That is the thing. Although we can see that it is still getting this thing and we are still able to see. Okay, what is this? Have they, why is everyone tweeting it out? Is it successful? See, we are getting the signal. What? Okay, what is happening here? Slev might be moving. Yeah, Slim is fine now. Looking, I think we can mark it as a success. Oh, thank you so much, Instance. If I pronounce that correctly. Total respect and admiration for your live narration and solo covering of this event. Excellent level of knowledge from you on this. Thank you so much. That's just I love to do this thing. And okay, we are getting the signal on the lev now, I guess. Lev 1 moving now, might be. Scott Tilley is here. Can you accurately compare SNR of both missions? Okay. Lev 1 might be moving to see the you know, taking Lev 1 does not have those cameras and all, but Lev 2 has. So Lev 1 and Lev 2 are in operation. They have landed. I'll declare they have landed successfully. That's it. I don't care about their orientation. It is on the moon. It is receiving it is giving out signal. So yes, it is fine. It is fine. Okay. There you go. It is successfully landed on the mission is accomplished. So guys, Japan, for me it is successful. I have enough proof for that. The Dopplers will not say anything wrong. We are still getting signal. Slim is fine. Here you can see the Dopplers of the LE1, LF1. Here the NASA is still, you can see the Deep Space Network, it is still receiving signal. It is still intact and it's working fine. So it is a success for me. And yeah, so guys, this is Japan has become the 5th country to land on the moon successfully. Now orientation, not so sure, but landed on the moon alive. Yes. Lev 1 alive. Yes. Talking about the orientation, but I think that's fine. That's fine. They did it. Japan did it on their first attempt. That too, this crazy maneuver which they were supposed to do, belly flop and all those things. So success, but no one is happy. Because they see Japanese people does not, you know, they do not what should I say, what I have seen in so many streams, right? They do not demonstrate their emotions or something like that. So whenever there is I have seen both success and unsuccessful mission from Japan. Whenever there is an unsuccessful mission, they become fully depressed. They'll feel like they have fully ashamed, and you can see in their eyes that they did not do as per the expectation. But we all know that is the case with the space missions, that those things are hard. So by judging their reaction from today, they were not looking happy, but they were not looking fully depressed also. That I can say, because I have seen them when the mission was fully unsuccessful. I remember there was one rocket launch which was unsuccessful, and I remember there was one. It was not even unsuccessful fully. It was like it was supposed to launch at that time, but there was some sort of issue with the rocket, and that caused an hot fire about. And we could see in the conference, in the broadcast also, that they were a bit what should I say, felt like very bad because of that. But I did not feel that today. So it has landed, but it has not, maybe they what they expected, that might have not happened. So yeah, kudos to them. Japan has become the fifth country to land. So I think I am safe to tweet it out, right? Yeah. Yep. They don't take it hard, hopefully. Good job. Okay, army reference. Great. I think I can retweet this part. On the moon. Yes. Not. That should be good enough. They read it. I'm not sure. Okay. It was neither a full success as estimated nor a failure as estimated. Now they are confused. They might be Christian. Yes. They don't have those emotions as such, but yeah, this thing was something. Not sure whether I'm following her though. So my take, it landed and rolled. Why? Landing too fast. Yes, landing and not shutting down engines immediately. Landing with too much lateral velocity. Angular momentum makes things roll further in low lunar gravity. If the orientation can be trusted, then SLIM is facing its solar panel westwards, meaning they have no sunlight right now, but they will be illuminated in a few days and some signs may be possible. We need to check to see what instruments may have been impacted by a rule like this. there you go, guys. The actual the internet rocket scientist has spoken. So this is what I also assumed, right? The two things, the landing too fast, landing and not, no, I don't think so. This I did not expect, but yeah, this might be the case. Landing with too much lateral velocity, this can also happen. But the angular momentum part, we could not see the from the telemetry, but again, we can't trust the telemetry because it has hit the ground and antennas might be messed up. But whoa, that was something. Okay, I think not sure when they will start this press conference. We can safely end this stream, I guess. Landing on aircraft without the wheels not down is still a landing. See, you land on when some issue happens, you land on the water also. So in that case, is it a successful landing or not? So see, the thing is, it landed there. I'm not, if I don't consider the orientation right now, let's just forget about the orientation. It landed on the surface of the moon. It is still intact. It is still able to give the signals. We can see the Lev 1 signal strong, the Slim signal strong, and we can see, yes, it is on the moon. The only problem is the landing part, the orientation part. And if we can see it here from this thing, we can see it is facing in this direction, the westwards. If the telemetry is supposed to be taken into account, then in that case, as he said, we need to see in my this thing also, the sun is over here. So when it comes on the upside, we should be able to light the solar panels and it should be fine. So in this case also, if the sun is on this side, it will lose the battery. In few days time, it will come on this side also, the sun, and it should charge it in that case. So that should be it. Slim has landed in a, that's what I am also saying. Great. What is this? Okay. All right. Now I'm just scrolling Twitter and nothing else. I think we can end the stream now. We can have to wait and see how if they'll what will happen in the press conference and get to know. So you can follow me on Twitter, guys. It's @RocketGyan. Here it's in the description also, so you can go and check my Twitter. I'll update it over here what has happened actually, but I think for me it is a successful mission, and yeah. See, I can wait. I am a person who would like to wait, who like to see from the official announcement also. But I'm also a person who likes to, you know, derive conclusions from the information that I have. So from the information that I have is that it is still giving out the signal. The Lev and the Slim is giving out the signal. Which means it is still intact. It is working fine. It has nothing like critical has been harmed. So we need to see, because in Chandrayaan 2 we know what has happened. We know that it actually crash landed on the surface of the moon. Bare sheet, we know it crash landed. So it no signal, nothing was coming. So yeah. And here also you can see DSN receiving signal. See, communication is the first thing to get picked up when something bad happens. So if communication is fine, that is a strong representation of the fact that it is still looking good. Yes, see, stable radio communication still continue. Okay, I think that should be it, guys. If you loved the stream, please give it a thumbs up, and if you want to support me, you can become a channel member or support me on the Patreon. Link is down in the description. It really helps the channel to stay alive, and I'll keep on improving the way I present the things. I hope you like the new format of me coming up and showing my face, right? So hopefully you liked it, and I'm happy that's in despite of such a crazy maneuver that the JAXA had to perform to land on the moon, they were able to do 95% of it. So I mean, it might not have that much of orientation which is required, but again, it's on the moon, it's alive. Lev 1 is alive. Lev 2, not sure, but it might be taking some pictures, right? We'll get to know from the pictures what is the situation of the lander for sure. But it is alive. It was going so perfectly fine till 50 meters, and after that also it was like, okay, we were getting some sort of acceleration, but it was good. And right now the engines are up, which it should not be, but let's hope for the best. I know that the JAXA's scientists are very intelligent. What I do, I'm not sure what is the reaction mass they have, that if they have a good reaction control system or some thrusters they can use to fire and move it to a correct orientation. That is still we need to see, because they do have thrusters. I'm not talking about the engines, but the thrusters which they can fire in some sort of sequence which can cause the lander to topple at the safe orientation. Not sure this can happen, but they need to assess the situation. They need to see what is the orientation right now, what is the situation right now, from the pictures, from the telemetry, from everything, and accordingly they can plan. And they don't have many days. Talking about the mission life of this, so Lev 1 and the Lev 2 both have around 40 minutes to 2 hours of battery life. They don't have any solar panels or nothing like that. So I don't think so it will be able to they will be able to do any maneuver right now, because if it actually makes sense to do it right now, because if there is any possibility to make it come back to the stable state, then if Lev 1 and Lev 2 are still alive, they can photograph the situations, the landing situation, and we can get to know, yeah, this is the case, it is fine right now, it's stable. But I don't think so they'll be in such a hurry to just give up, do it out of haste to get the photographs. So so basically, yeah, we need to wait for them to analyze. Hopefully, not sure, but still this can happen. They can do it. They can fire certain thrusters, but again that would depend on what is the mass of this thing, and whether it will have that much of force to topple it in the stable direction. We need to see. There are so many things which are in place, stake right now, but it has landed. Japan has become the 5th country to land on the moon safely now, irrespective of the physical orientation. Condition is perfect, condition is intact. We can see the signals. Lev 1, Lev 2. Lev 1 is performing fine. Slim is giving out signals. That is enough for me to say, Japan, you did it. You have made your country proud, and everything is awesome. I know again here, if we compare it to ISRO's Chandrayaan 3, right, then in that case we were having that was a big flawless mission. It was a totally a flawless mission, and it was something which is supposed to be I mean, again, China's Chang'e 5 mission was also a flawless one. So but again, moon is hard, space is hard. They attempted, if they attempted to do it on the normal grounds, flat surface, as well as a normal conventional landing, I'm damn sure they were successful, because till 10 meters 15 meters it was working fine. At that belly flop only some issue happened. So, and yes, the fuel should have been around 10 kgs or so, but that was also more, so that might have caused some sort of calculations issues. Not sure, but because of that momentum and the moment of inertia, because of more mass, momentum and the moment of inertia increases. So there is that. Okay, this one was the most fun ones. Okay, nice, cool. Thank you so much for tuning in. We'll okay, next mission is when and of what. I'm really sorry guys that I don't stream that much, because the Exim Space Mission 3 I was supposed to stream, but I do have my own work, and the work is something which I can't what should I say, ignore, right? So I'll try to, whatever is the main missions, I will definitely try to stream those, so don't worry about it. So next mission is actually going to be it's the Starlink. Then we have from China Kinetica 1, the flight number 3, but I don't think so we'll have a flight live stream for that. The Virgin Galactic is launching their one, but other than that we will have the main mission will be on January of 27 for 4 of a kind Electron launch, and the Cygnus CRS-2 is also there January 29. Okay, we do have some time, we'll see. I think that should be it. Let me just check whether the press conference has begun or what. No. And one last time checking this thing. Okay, that should be it then. Cool. Thank you so much for tuning in. Name of the song, which is I don't think so. That is some lo-fi tunes which I liked and took. So not sure the name. I don't know the name of it, but yeah. Okay, thank you so much for tuning in, guys. I hope you liked the stream. If you did, give it a thumbs up, and if you want to support me, do consider becoming a member and a Patreon. So thank you so much for tuning in. Until then, this is Piyanshu Rohila. You just saw Rocket Gyan. Stay safe, stay healthy, and bye-bye.